All right, as we continue to factor quadratic expressions that now have numbers in front of x squared, the special factoring patterns that we met in the previous lesson still apply, being the difference of two squares pattern and the perfect square trinomial pattern. Now, again, recognizing squares and recognizing patterns is a huge time saver. You could come up with the right answer if you were to walk your way through using the British method that we just practiced. However, the British method can be pretty time consuming, as I'm sure you're finding out. So any method that I can use that will help solving time is one that I would be interested in learning. I hope you are too. So the difference of two squares pattern, if I have a square at the beginning, a square at the end, and a minus in the middle, it factors into a binomial or two binomials with the roots of the first term and the second term in each, but different signs in between. A plus sign here, a minus sign here. So key is being able to recognize perfect squares. 16 is perfect square, so is x squared. 81 is perfect square. There's a minus in the middle. I don't need the British method here because I recognize the difference of squares. I know that the first term in each of these binomials needs to be 4x because that's what is the square root of 16x squared. I know the second term in each of these needs to be 9 because that's what the square root of 81 is. I know that I'll have a plus in one and a minus in the other. Quick FOIL to check it. 16x squared minus 36x plus 36x is 0. There's nothing there. And then 9 times negative 9 is negative 81. Fantastic. The other pattern that works for these still is the perfect square trinomial pattern. Maybe I notice that I have a square at the beginning. Maybe I notice I have a square at the end. If that's the case, rather than dive right into the British method again, which would work but takes some time, I'm going to at least attempt to write this as the square of a binomial, remembering my work with completing the square and all that other stuff. So if this really is a perfect square trinomial, the first term of my binomial would need to be the square root of the first term. So 2x, which is the square root of 4x squared. Second term will be 3 because that's the square root of 9. It's plus 12x. I'm going to guess this is plus 3. And then I'll just check this mentally to make sure it works out. Let's see. To square a binomial I, square the first term. Good. Multiply the two together. That's 6x. Double it. That's 12x. Bingo. Square the second term where I'm going to get 9. Perfect. And the perfect square trinomial, even if I have a negative second term, might still work. 25x squared is a square. 16 is a square. Is it worth a shot? Absolutely, because it will save us some time. I am willing to bet that 5x goes here and a negative 4 goes here. And then if I work my magic and square this binomial, I'll have 25x squared. Multiply the two together, double it. It's going to be negative 20x. Doubled is negative 40x. Perfect. And negative 4 squared is going to be 16. Now, sometimes I shouldn't say sometimes, every time you're asked to factor something, you should always look to do this first. Factor out a monomial. Another way we think about this is as a GCF, a greatest common factor. If there's a greatest common factor, something that all of your terms share, always factor that out first because it'll make the rest of the factoring you have to do that much easier. Looking at these three terms, what do they share in common? Well, 6 and 15 and 9 all share a factor of 3 in common. They also all have the same variable because they have a p. The most I can take out of these would be p to the first. I have 3 of them here, 2 of them here, 1 of here, so I can take out 1 maximum. After I factor out 3p, I am left with 2p squared plus 5p plus 3, close parentheses. Now, that's not the only thing I need to do. I factor out a monomial, but I still have a trinomial, and that's something I need to factor all the way through. So there's a number in front of p squared. I'm going to go ahead and use the British method just within the parentheses here. So 6p squared is my first product. Factor that. Factors of 6 add up to 5. Well, it's going to be 2p and 3p. Bring down the outside terms. We got a 2p squared plus 2p. And we got a 3p plus a 3. 4 terms means I can group. First pair, second pair. Greatest common factor of the first pair is going to be 2p. Out it comes. Leaves me with p plus 1. Greatest common factor of the second pair is going to be 3, positive at that. Leaves me also with p plus 1, which is nice. So my factors are p plus 1, the common binomial factor, and 2 plus 3, the leftover factors. And don't forget the fact that we took out a 3p way back here at the beginning. It's still part of my factored expression. So 3p and all this stuff put together, there's my answer. Now for this next one, again, factoring out a greatest common factor, I notice that the 4 exists in all these. I'll take out a 4, leaves me with x squared plus x minus 1. And in this case, that's all we can do. This one's not factorable from here. If you notice, if I take 1 times negative 1, okay, I get negative x squared. There's no factors of negative 1 that add up to positive 1. So this one cannot be factored any further. You're not going to guess and check it. You're just going to say, you know what? It's factored because I took out the greatest common factor, and that's all there is to it.